Welcome everyone for this new SIPTA seminar, so the one of May. And without further ado, I will let Kevin introduce now in details, and I hand him the floor. Kevin, you're on.
Okay, great, thanks. Yeah, so it's my pleasure to introduce S.Zhang, who is, I think, currently assistant professor at UC Berkeley. And so I guess her research interests are sort of broadly in formal epistemology, decision theory, philosophy, and foundations of probability. I think also some research interests in Chinese philosophy, although I don't know as much about that. So I'm not going to try to, summarize all of the things that Snow does. Like I think she does a lot of very interesting, both technical and philosophical work. But I'll just mention like sort of two themes. So one is kind of, I guess, understanding, proving things about, and generalizing updating rules. So Jeffrey conditionalization, imaging, all of this kind of stuff. That's something that I'm also very interested in. So some overlap there. And the other main theme, or at least one other main theme that is going to be relevant to the talk today, is the stuff on linear pooling, sorry, not linear pooling, pooling, expert pooling, or like opinion aggregation stuff. So both kind of impossibility theorems for precise attempts at coming up with pooling rules that sort of satisfy certain kinds of plausible constraints, but also I guess showing that there are imprecise pooling rules. So I think I believe this is going to be a continuation of work that she presented at the EPIMP inaugural conference, sort of similarly titled talk, showing some of the impossibility stuff for precise pooling rules, and then developing imprecise pooling rules. But I'm very excited to see what the talk today is going to be. So I think that's probably more than enough for me. But yeah.
Thanks so much, Kevin, and thanks, Sebastian, and all the organizers for inviting me. Let me just start by sharing my screen. Kevin mentioned this talk is going to be a continuation of the work that I presented, I guess, 3 years ago at the inaugural conference of epistemic utility and imprecise probability. In fact, apologies in advance. So actually, I haven't had opportunities to think a lot more about that topic. So some of the materials will overlap with the things that I presented before, but hopefully there are something new. I should also say that I feel like a lot of people in this room probably know a lot more about this topic than I do. So I won't be surprised, as before, that perhaps what I'm reporting here is just old news, or my questions are already solved in the literature, in which case I hope this will just be an opportunity for people to exchange information about this topic. Okay, so great. So the problem, I think for this group, probably it's the problem needs little introduction, is the problem of probabilistic opinion pooling. Just for concreteness, I'm going to focus on a very simple setting, which is I'm going to use this as an example later on as well for illustrative purposes. So let's say that the two of us are deciding where to go for dinner. Well, for me, maybe it's deciding where to go for coffee. And we're deciding between two restaurants, A and B. Both of us think that only one of them has seats. Neither of us made reservations beforehand. But we have different opinions about which restaurant has seats. So say you are 80% confident that there are seats at restaurant A, but not B, and I have the opposite opinion. Okay, so far so good. Question, what do we think as a group? And also, perhaps more importantly, where should we go for dinner? Should we go to restaurant A, restaurant B, flip a coin, so on and so forth? So this is the general motivation for the formal problem that I'm going to define shortly. Given an individual's opinions, for now, let's focus on finite groups for the purposes of this talk. What is their opinion as a group, collectively speaking? And this problem is important and arises in a lot of contexts, including policy making, figuring out what is the scientific consensus on a number of questions, such as effectiveness of vaccines or certain medical treatments. And also, perhaps many of you have experienced in department voting, we want to pool our opinions about the competence of a particular candidates or who to invite as a speaker, so on and so forth. So that's the general problem that I'm interested in. Let me make things a bit more precise. And for now, I'm going to focus on the simple setting where the individual's opinions are precise probability functions. Of course, the hope is that in a moment, we're going to generalize this to imprecise probabilities as representations of individuals' opinions. So let's fix a finite sigma algebra of propositions, which we're going to call as the agenda. And notationally, I'm going to use delta F to denote the set of precise real-valued probability distributions over F. And delta NF would just be the n tuples of probability distributions over F. Each individual probability function represents the probability of a particular individual member in the group. And finally, this is the most crucial thing, we're interested in how to figure out what is the probability of the whole group given the probabilities of its individual members. In other words, formally speaking, we're interested in defining a function f that takes as input a sequence of probability functions, the profile of the group, and outputs a single probability function, which represents the opinion of the group. So as you might observe at this point, this definition of the pooling function assumes that the opinion of the group is also representable by a precise probability function. Again, for those of you who attended my talk 3 years ago, you know that the hope again is to relax this assumption later after realizing how hard it is to represent the opinion of the group as a single probability function. So we're going to relax the assumption in a moment. So this is the preliminary setup. And then the problem now becomes the formal question, what is the correct F? So before I move on, let me just take a step back. This is probably going to be the most philosophical part of this talk. What is the question that we're asking? I like this list of disambiguations given by Karl Wagner in his 2010 paper. And he acknowledged that this is still an incomplete list, but I think it's a helpful guideline. So there are at least, as he points out, there are at least 5 different things that we might be interested in using this F function to represent. First, we might be interested in figuring out the rough summary of the current probabilities of the n individuals. That's sort of what I'm asking when I ask what is the probability of the whole group as a collective. But you might also be interested in a related question, which is what is a compromise adopted by the individuals for the purpose of group decision making? So for example, when we're deciding where to go for dinner, then seems like the probabilities we as a group assign to the restaurant, which restaurant has seats, is closely related to the question, well, where should we go for dinner? Maybe we're going to use our group probabilities as an input for deciding that. So thirdly, we might be interested in figuring out a rational consensus to which the individuals revise their probabilities after discussion. So this is when each individual tells the other what their probabilities are, and they then update their individual probabilities given the opinions of the other group members. Fourth, the opinion of a decision maker external to the group, which they should adopt after being informed by the opinion of the individual members. And as you can imagine, this could arise. This arises frequently in the policymaking context, where the policymakers consult the scientists about their opinions, and the hope is that they then could update their own individual opinion as an external member to the group about the relevant subject matter. Lastly, we could imagine the F function being used to figure out the opinion of an individual member in the group, which they should adopt being informed of the n-1 opinions of their epistemic peers in the group. This is closely related to the question 3, but here we're assuming that all the group members are epistemic peers, and in particular, they might share the same information to begin with. Okay, so these are 5 different questions. And the most important thing I want to highlight is that it's not obvious from the get-go that these 5 questions admit of the same answer. The same F may not be useful or appropriate for all 5 questions. In particular, for those of you who are sympathetic to Bayesian epistemology, I might count myself as one of them. Through question 3, 4, 5 have an easy answer. The individuals should update their own opinions. The individuals should update on the other people's opinions, be them the opinions of their peers or the opinions of the external experts, by Bayesian conditionalization. And then the pooling function could be used as a kind of heuristic shortcut for approximating Bayesian conditionalization if we think that Bayesian conditionalization is too complicated, or it might be viewed as a rational constraint on the particular agents prior. So for the purposes of this talk, I'm actually going to set aside 3, 4, 5 for that reason. I think it's a complicated question how the answers to 3, 4, 5 should relate to Bayesian epistemology, viewed as an ideal standard for rationality. Instead, I'm going to focus on question 1 and secondarily question 2. So I'm mostly interested in using F to present a rough summary of the current probabilities of the n individuals. And maybe this summary could be used as the input to the group collective decision-making procedure. I think there are a lot of interesting philosophical questions to be asked at this point, how these 2 questions relate to each other and how they are then related to 3, 4, 5 for both ideal and non-ideal agents. But for now, I'm just going to set aside 3, 4, 5 for the purposes of this talk. Okay, so that's the preliminary setup. Here's the plan for the rest of this talk. So I've told you what the problem is. Now I'm going to first look at some impossibility results, which I don't know why it's not showing up here. So I'm actually going to first review some basic impossibility results in the precise setting, and then move on to imprecise pooling rules, in particular focusing on the a particular pooling rule advocated by Steward and Quintana, which they call the convex imprecise pooling rule. And the main contribution of this talk, of my work, again, for those of you who knew about this, is now news, is an axiomatic characterization of convex imprecise pooling rule. The new ingredient, which I'm going to add in this talk, is relating this result to a different characterization result by Casanova 2021, which they obtained the axiomatic characterization of democratic social rules. And if we have time, I'm going to generalize this result and the correspondence between these 2 axiomatic characterizations to imprecise aggregation, aggregation of imprecise probabilities. And if we have more time later, I'm going to talk about briefly the epistemic utility argument for aggregation of precise and imprecise probabilities. So that's a rough plan. Okay, so impossibility results. So in the literature, aggregation, it is filled with impossibility results. Here I'm going to focus on the perhaps the most well-known impossibility result, which has 3 axioms. The first one is called systematicity, which says basically that in order to figure out the opinion of the group about a particular proposition, all you need to know is the opinion of the group's members, the group members' probabilities about that particular proposition. And also, with some extra assumptions, we also want to do it uniformly. So it doesn't actually matter which proposition we're looking at. For any proposition, we're going to use the same function to figure out what is the group's opinion about that proposition, given the individual members' probabilities about that proposition. So this is called systematicity. And in particular, one famous result due to McCowan is that irrelevant alternatives, which is the first part of what I just said, the group member's opinion about a particular proposition only depends the group's group's probability about a proposition as a whole only depends on the group members' probabilities about that proposition, and it doesn't depend on their probabilities about any other propositions. And also zero preservation, which says that if the group members all assign probability 0 to a proposition, then the group as a whole assigns 0 to that proposition. An interesting result due to Matanwe is that these two axiomatic constraints are equivalent to systematicity. Assuming that, by the way, there are at least 3 possible words. This is something we're going to assume throughout. And also, by systematicity, it turns out that the only rule that satisfies this constraint is linear averaging. So when you pull the individuals' probabilities into one single probability function, the only way to do it is systematically is to take a linear average of the group members' probabilities. So while you might think, as Matanwe did when he first proved the result, that this is a powerful argument for linear averaging, some people find it counterintuitive. And in particular, one nice constraint you might want to impose on the pooling rule is that it should commute with Bayesian conditionalization. That is, it doesn't matter whether you pool the group's opinions, group members' probabilities first and then update it on a piece of evidence by conditionalization, or you feed the group members each individually that same piece of evidence first and then pool their posterior probabilities by the same pooling function. So the thought is pooling should commute with updating, and this is not the case for linear averaging. Here's a concrete illustration of why that is the case. So let's go back to the restaurant case. Let's say A stands for the proposition that restaurant A is open, but B is not. And similarly, B is the proposition that restaurant B is open and A is not. And let R be the proposition that it will rain tomorrow. So let's say P1 and P2 are our respective prior distribution. So I am 0.8 confident that A is open, whereas you are certain that A is not open, B is open. And this is also, and then on the other hand, both of us, so I am 50-50 between whether it's going to rain, and you are 0.8 confident that it is going to rain. So if we do equal weighted averaging between our two probability distributions, we would obtain the probability distribution P given by the third row of the table. And then suppose we learn that restaurant B is open, we update this collective probability function by conditionalization on B, then we will get the last row of the table, which is the result of pooling, then updating. So in particular, we're going to collectively assign 0.75 probability to the proposition that B is open and it is going to rain tomorrow. Okay, so far so good. Now, what if we each update on the proposition that B is open, restaurant B is open and A is not, and then pool our probabilities by linear averaging, and in particular, equal weighted averaging? Well, here's the result. So again, crucially, the last row is what we would get if we first update and then pool by linear averaging. And as you can see, the number is different. We're going to collectively assign 0.65 to the proposition that B is open and it's raining rather than 0.75. So this is a concrete illustration of how pooling after updating is different from updating after pooling when we are pooling using fixed weight linear averaging. The numbers could get even more different in some other cases, but I hope this communicates the point. Okay, so what should we, how should we respond to this impossibility result? To state it concretely, so this is due to Russell et al., there is no non-dictatorial rule that is systematic and commutes with Bayesian conditionalization. A side note, one naive thing that I thought would work to escape this impossibility result is to relativize the pooling function to evidence profiles. Turns out that that would not work. So if you're interested, I'd be happy to talk about why it wouldn't work during Q&A. Roughly speaking, it has to do with the fact that we have to relativize the pooling profile to the probability profiles rather than the evidence profiles. If we think that the evidence is compatible with a number of probability profiles that assign probability 1 to the evidence, then relativization to evidence profiles wouldn't work. Okay, so it seems that now we have only 4 options on the table. So one is to reject systematicity. This is indeed Russell et al.'s proposal. And I should say that I'm partially sympathetic to this idea. And I think in particular, the linear averaging, even though linear averaging doesn't commute with Bayesian tangentialization, if we allow the weights that we assign to the individual's probabilities to vary depending on what we just learned, then it turns out that linear averaging can be made to commute with Bayesian tangentialization. And I think the ways that we're adjusting the weights do make sense. So I do think that there is a sense in which we should escape these impossibility results by rejecting systematicity, but I'm not going to discuss that option for now. Here are some other options. We could reject Bayesianism. So maybe the pooling function shouldn't commute with conditionalization, but some different updating procedure. Or maybe we can just reject commutativity altogether. I think this is especially attractive if all we want is a rough summary of the A individual's opinions, and we might think that should be sensitive whether or not we fed the individual's evidence first or after we update, we put their probabilities together. But the option that I'm going to focus on for the rest of this talk, I'm about 15 minutes in, so I better start talking about the imprecise probabilities. So I'm going to focus on the way of escaping the impossibility results by allowing the pooling function to be an imprecise pooling function. That is, it might map probability profiles to a set of probability functions rather than one single probability function. And here's one way to restate the impossibility result. If we want a pooling function that is systematic, non-dictatorial, and commute with Bayesian tangentialization, then it must be imprecise. So we get a necessary, sufficient condition for imprecision. Okay, finally, imprecise pooling rules. So following the axiomatic tradition, in the imprecise setting, I think the naive idea is to start out with some axiomatic constraints and see what pooling rule these constraints force us to adopt. And maybe it would be helpful to just put some options on the table. So here are some options that I came up with when thinking about this question. Once we are in the imprecise land, we have embarrassment of riches. There are so many things that we could do here. One very naive thing to do is to just do what I call listing. When I'm given a profile of individual probabilities, the groups of probabilities just represented by the set of probabilities consisting all and only the individual members' probability functions. We could also do something that I alluded to before, which is convex imprecise pooling, which takes an individual probability profile and outputs the convex Hall of those probability functions. That is linear combinations of those probability functions where the coefficients are between 0 and 1 and sum up to 1. We could also do oligarchy, which is to take the convex Hall not of every single probability function in the profile, but only some subset of probability functions in this profile. Here, I used the particular example of only taking the convex Hall of the first two individuals' probabilities. Two more examples. This is what I call the trivial pooling rule, which is to say, I don't care which what the individual members of the group thinks. Instead, I'm always going to output the trivial set of probability functions, namely every single probability function over the state space. Probably not something that we would want to use, but it would be interesting to ask what kind of axiomatic constraints could rule this out, because it seems like it could satisfy a lot of desirable properties. Here's the last one. I think actually I got I started thinking about this rule because of someone's question during the Q&A after my talk 3 years ago. So sorry, I forgot who brought up this possibility, but it's a very interesting example. So this is what I call explosion, which says that if every single member of the group agrees, then I'm going to take that unanimous probability function as the probability function of the entire group. Otherwise, I'm going to do explosion. Whenever there's disagreement, then the group's probabilities is represented by the trivial set consisting of all probability functions over the state space. Okay, so these are options. Clearly, they're not exhaustive, but I think that gives us a sense of the kind of things we could do when we're in the imprecise setting, which makes the question a bit more non-trivial. So if we like one particular imprecise pooling rule, say, for example, the convex imprecise pooling rule, what are the constraints that could rule out all but this pooling rule as the desired pooling rule in this case? Okay, so that's what I'm going to do here. Here's the result from Steward and Quintana, which shows that convex imprecise pooling does satisfy the properties that we wanted from the precise pooling rule. And unfortunately, we couldn't have those, but we could have them in this imprecise setting. And it turns out that the convex imprecise pooling rule actually satisfies a stronger property, which is known as external Bayesianity. And roughly speaking, it just says that the pooling function is a commutative. Sorry, I realize there's a typo here. It should just be the normal profile. But the rough idea is that the pooling function commutes not only with Bayesian conditionalization, but also likelihood conditionalization, or equivalently, with some small caveat, Jeffrey conditionalization. So not only that, when each member of the group learns a particular proposition, it doesn't matter whether they learn the proposition first before pooling, or you pool their probabilities first and then update their relative opinion using by Bayesian conditionalization. The commutativity also holds when we update each individual member's opinion by Jeffrey conditionalization. And here, by updating a set of probability functions, I just mean updating each member of that set using the same updating procedure. Okay, so that's external Bayesianity. But does that pin down a particular pooling rule given our list? Well, if you think about it, clearly not. In fact, all the other rules we have considered on the previous slide satisfy external Bayesianity. I'll leave that as an exercise if you're interested. So that makes me start wondering what other constraints we could use to rule out the pooling rules on the list. One constraint is what I call general systematicity. And as you can see, it's a straightforward generalization of systematicity that we considered in the precise setting. So in this case, we're saying, in order to figure out the set of expectations that the group adopts towards a particular random variable, all I need to know is the group members' individual expectation of that particular random variable. And moreover, we can do it uniformly, so irrespective of which random variable we're considering. We use the same function, which takes as input the individual member's expectation of that random variable and outputs a set of real numbers which corresponds to the group's expectations of that random variable. Okay, so if you think about it for a second, it turns out that this particular constraint rules out both the trivial pooling rule and the explosion pooling rule. And the reason is that, well, think about the special case when you ask for the group's opinion about the tautology. Well, each individual probability is going to assign one to the tautology proposition, and so does every single probability function that could be a member of the output of the pooling function. Which means that when you feed a sequence of 1 to the function g that exists due to general systematicity, it should always output a singleton 1. But as we said before, general systematicity also says that we don't care whether we are pooling the expectations of random variable y or random variable x. As long as the group members agree on their expectations, we're going to use the same function to pool their expectations. So that means that whenever the individual member assigns expectation 1 to some random variable, every single member of the group, every single probability function that is in the set fp1 to pn should also assign expectation 1 to that same random variable. And that rules out the trivial pooling rule as well as the explosion pooling rule. Okay. By the way, you might think that suggests that the general systematicity might be too strong. I'm partially sympathetic to that thought. We can totally discuss it during Q&A. But for now, it's interesting that this is the constraint that rules out those two interesting pooling rules. Okay, I actually don't know what non-ad hoc constraint could rule out listing. I think that's also an interesting open question. For now, I'm going to rule out that particular pooling rule by assuming that the output of the pooling function should always be a closed and convex set of probability functions. There are, as many of you know, interesting arguments both for and against this assumption that the imprecise the set of probability functions that represent an agent's opinion should be a closed and convex set. Well, we can discuss about it during Q&A as well. So that's how I'm going to rule out that particular option, which leaves two pooling rules on the table. One is the convex IP, that is what we want, and the other one is the oligarchy pooling rule. And as you might expect, it's pretty easy to rule out the oligarchy because we can, the natural thing to do is to assume that the pooling rule should be anonymous. That is, it doesn't care who holds which probability functions. Formally speaking, whenever we have a permutation, a profile that is obtained from another profile, by permuting the probability functions, the output of the pooling rule should be the same. In the precise setting, that would force the weights to be the same. In the imprecise setting, that would rule out taking the convex Hall of a proper subset of the individual members' probability functions. Okay, so we ruled out everything on our list, but of course our list is incomplete. So maybe there are still some other pooling rules that satisfy those constraints, and yet we have not considered. Luckily, it turns out that this is not the case. Convex IP is equivalent to general systematicity, external Bayesianity, and anonymity under certain structural assumptions. One is the assumption we have already mentioned, that the pooling rule outputs closed and convex set of probabilities. And the other one, which I hope I could find a way to relax, but I still haven't quite figured out how to do it. It says that the atoms of the agenda should be at least as great as the number of individuals in this group. And you'll see, I'll give you a proof sketch. So you'll see in a moment why this assumption plays a role in the proof of the theorem. Okay, so here's the proof idea. First, by general systematicity and anonymity, of course, we can show that the equal weighted average of the group members' probabilities would always be a member of the output of the pooling function. And roughly speaking, that's because we can sort of assume that we have a precise probability function, and that satisfies precise pooling function that satisfies these two constraints, and then just drop the precise constraint. So by the previous result, we have that the equal weighted average of the group members' probabilities is always a member of this set. And then by external Bayesianity, suppose that we're looking at, and this turns out to be the central trick of the proof, suppose we're looking at a set of group members who are extremely opinionated. Their probabilities are basically Dirac functions that puts all the probabilities to one single possible word. Let's look at those profiles. And it turns out that by external Bayesianity, if a probability function is a member of the representer of the group's probabilities, where the group consists of individuals holding these extremely opinionated probability functions. And we have another probability function Q that is absolutely continuous with P. That is, it assigns probability 0 to an event only if P assigns 0 probability to an event. Then we can show that Q would also have to be a member of this representer. And that's because of the commutativity constraint. So in particular, since by the previous result, the equal weighted average of the Dirac measures would always be a member of the representer. So basically, any other non-trivial convex combinations of the Dirac measures would also be a member of the representer. Then by the assumption that the representer is closed and convex, we can show that in this special case, when all the group members have extremely opinionated probability functions, their opinion as a group must consist of all and only convex combinations of those Dirac measures. And lastly, by general systematicity, once we have this particular result on at step 3, then, and this is where the last structural assumption kicks in, we can just look at the derived measures expectation of a particular random variable and use that to pin down the G function, which features in the general systematicity constraint. So that gives us that with a bit of work, the representer for any group of probability functions has to be the convex Hall of those probability functions. Okay, sorry, that was a bit too quick, but I hope this could give you a sense of how the proof works and where the assumptions are needed. I do think that maybe there are some other ways of proving this result, and in particular that would help us get around certain assumptions. So if any one of you has any ideas, I would love to hear them. But this is the best I've tried so far. Okay, so I think I have, Kevin, is it right that I have 10 more minutes?
Yeah, I mean, I think certainly, yeah.
Okay, great. Thanks so much. So now I'm going to make a connection between this axiomatic representations of convex IP rules and a recent result by Casanova and et al. In their 2021 paper. So let's start with coherent set of desirable gambles. And here's the definition. So a gamble is just a real valued function, or alternatively, as we put it, a random variable. And we say a set of such gambles is coherent if it satisfies the following 4 constraints, which probably are more familiar to people in this group than it is to me. I'm sort of learning this very recently. So it is coherent if the 0 gamble is not in this set, but any non-negative gamble that is not 0 would be a member of this set. And also this set is closed under addition and multiplication by positive coefficients. So this is a coherent gamble. And we say that such a coherent set is maximal if for every random variable that is not 0, either x is in this set or is negative x is in this set. And let D be the set of coherent set of desirable gambles. A social rule is just a function that maps a profile now consisting of a list of coherent set of desirable gambles to a coherent set of desirable gamble itself. And in particular, by the way, these definitions are all from the Casanova 2021 paper. So if I made any mistakes, I'm completely responsible for that. So yeah, please point this out if anyone has any questions. So we say a subset of the groups is an oligarchy for a particular pooling function, a particular social rule, if it satisfies the following 2 conditions. One is that a gamble that is desirable for every single individual member of the oligarchy is also desirable according to the group. And also, if a gamble is desirable for some particular individual member in this group, then, oh, sorry, I forgot negation here, then it's not the case that the group as a whole accepts its negation. So intuitively, that the first condition corresponds to a Pareto principle. If everyone thinks that X is desirable, then so does the group. And the second one corresponds to veto power of individual member of the group. Each individual member has the power to veto a particular gamble by saying, I want this gamble, so this the group as a whole can't accept the negation of this gamble. And we say that the social rule is democratic if the entire group is an oligarchy. Okay, so the one cool result that Casanova et al. Proved in their paper is that weak Pareto, independent of irrelevant alternatives, and anonymity jointly entails that the social rule is democratic. Okay. Just by looking at the constraints, you might already start wondering, well, it seems that this has a lot some overlaps with the constraints that we have looked at before. So what are their relationships? Well, here's one way to make the relationship precise. First, quick observation. if the individual members' desirable coherent set of desirable damples are maximal, which means that the probability representers that give rise to this coherent set of desirable damples are themselves precise, and also gamma is democratic, then gamma of the profile would just be the intersection of the coherent set of desirable damples. In general, this would not be the case. We're going to see an example shortly. But in this particular case, where D1 to Dn are maximal, it is indeed in virtue of the whole society being an oligarchy for the pooling rule, it turns out that the pooling rule has to output the intersection of the coherent set of desirable damples that are in their input. Okay, so now we can see, think of correspondence between the two setups in the precise case. So remember, before we start out with a profile of precise probability functions, and then ask for a pooling rule that maps this profile to possibly a set of probability functions. On the other hand, now we're in the setting where we start out with a set of these coherent set of desirable damples, use a social rule to map it to another coherent set of desirable damples. And basically, with a little bit of thought, you can see that this diagram commutes. That is, if the pooling rule, that is the convex imprecise pooling rule, which maps the profile to the convex hull of those profiles, corresponds exactly to the social rule that is democratic, which then in the precise setting maps the profile of coherent set of desirable damples to their intersections. I don't know if I have the result here. Oh, sorry. And basically, the only step left proved is the correspondence between the intersection of the profiles coherent set of desirable damples on the one hand, and the convex hull of the probability profiles on the other. I can talk about it later. So basically, the diagram commutes, and that raises an interesting question, I think, which is one of the main open questions I'm going to leave. I still don't know the answer to. So remember, the axiomatic constraints that we use to get convex imprecise pooling is basically general systematicity, external Bayesianity, and anonymity. Whereas in the democratic setting, what we have is weak Pareto, anonymity, and independence of irrelevant alternatives. So clearly, the anonymity constraints correspond to each other. And intuitively, general systematicity also gives you something like weak Pareto. But on the other hand, it's much stronger than weak Pareto. So one question is, what exactly is the relationship between external Bayesianity plus general systematicity on the one hand, and this is constraints on probabilistic pooling, and IIA on the other hand, which is a constraint on the desirable damples pooling? So I think that's a very interesting question. I don't know the answer to that question. If anyone has any thoughts, I would love to hear them. Okay, I think I have a little bit more time, so let me just quickly, oh, do I? Actually, I should chat with Kevin. Okay, maybe I'll just squeeze in a bit more about imprecise aggregation. So clearly the natural question to ask now is, well, what about the imprecise setting? So suppose the profile consists of not n precise probability functions, but n sets of probability functions. What should we do for the probabilistic pooling side? Well, the previous diagram actually suggests a natural answer to that question. Well, just find a pooling rule such that the following diagram commutes. And in particular, whatever constraints that we want to impose on the social rule, we can probably find an analogous set of constraints on the pooling rule, and that will give us the desirable pooling function, which corresponds to the desired social rule. This is more like a systematic proposal rather than a concrete proposal, because it depends on what axiomatic constraints we want to impose on the social rule. One naive idea is that, well, we have from before the three axiomatic constraints that Casanova et al. Proposed: weak Pareto, anonymity, and IIA. So maybe we can just do that. And by the way, those three constraints apply to any coherent set of desirable damples, maximal or not. So in particular, they would give us a way of pooling imprecise probability functions, which in themselves give rise to those coherent set of desirable damples. So I think that's a very natural thought. Here's a small wrinkle with that proposal. So remember, our previous correspondence result relies heavily on this lemma, which is that if the individual coherent set of desirable damples are maximal and the social rule is democratic, then we have this precise formulation of the output of the social rule, which is just the intersection of the coherent set of desirable damples. This equality does not hold when the individual coherent set of desirable damples is not maximal. And instead, more generally, we can only show that the following, it is sandwiched between two sets. One is intersection, which is given by the Pareto, and the other one is intersection of the negative gambles, negative of the gambles acceptable to the individuals to the complement. Sorry, I shouldn't pass that out loud, but you get the idea. So those two upper and lower bounds correspond precisely to those two constraints, oligarchy. And if you think about it, that would not be that would not correspond to the convex imprecise pooling rule. Instead, any pooling rule of the following form, that is, when you pool a set of probability functions, P1 to Pn, what you do is to take a convex Hall of S1 to Sn, where Si is a subset of Pi. Any such pooling rule will give you the set of desirable gambles that satisfy the relevant constraint. And you can also see why in the previous precise setting, we do have a precise correspondence, and that's because each P1 to Pn, they are precise, so they are singletons, which means that there's only one subset, non-trivial subset of the PIs. But in general, when we're putting imprecise probability functions, we have many options. Okay, so the correspondence doesn't hold precisely. However, and here's where I'm going to end on, you can show that CIP does uniquely satisfy the following axiom, which pin down it as the unique pooling rule for pooling imprecise probability functions. And this is what I call order independence. It does require generalizing the framework a little bit. So we're considering basically pooling probability profiles of different sizes, not only just a group of a particular size, but group of any possible finite size. And the rough idea behind order independence, together with anonymity, is that basically it doesn't matter whether we pool a subset of the group first, and then treat that as a particular individual, and then pool the entire group together, the rest of the group together with that subgroup. So that's one approach. So the thought is that give you the same result as just pooling the whole group's probabilities together. So that's what I call order independence. And that does pin down CIP as unique pooling rule for pooling imprecise probability functions. Open question, is there a similar axiom for social rules? And in particular, would that give us the following equality? Whenever we're pooling coherent set of desirable damples, we just take their intersections. I don't know the answer to that question. Maybe someone has already figured it out, in which case I love to hear them. So here's just to quickly conclude, I give you an axiomatic characterization of convex imprecise pooling and show that it's basically the same result as the result by Casanova 2021, where they formulated the result in terms of pooling coherent set of desirable gambles. However, there is that correspondence gives rise to the question, what is the relationship between these two sets of axioms on probabilistic pooling functions on the one hand, and axioms on the social rules on the other? And in particular, what is the relationship between external Bayesianity, general systematicity, and IIA? And also, I'm curious, some other open questions, further generalizations to the imprecise pooling related to the open questions I mentioned before. And lastly, I think, especially for people who are interested in probabilistic pooling, instead of asking when we get impossibility results in the imprecise context, we can ask a similar question: what is the necessary condition for kind of triviality results, where we have to include every single member of the profile as a part of the representer for the group's probabilistic opinions? Okay, so that's the end of my presentation. Thank you so much for your attention.